Welcome back, everyone. Today, we're diving into a brand new explainer on some seriously groundbreaking research out of NVIDIA. If you've been tracking the rise of frontier AI models, moving from massive, dense transformers over to these incredibly intricate mixture of experts architectures, then you already know that scale is literally everything. But here's the catch. What happens when the very engine driving that scale actually starts to sputter? We're taking a look at a fascinating paper called SOAP, Muon, and Beyond, Pushing LLM Pre-Training Scales. And let me tell you, it is a thrilling look right under the hood of deep learning optimization.
So, let's just jump right in and ask the billion-dollar question that AI researchers are sweating over right now as models scale up to these unprecedented sizes. What happens when the algorithm powering the world's largest AI models finally hits a wall? Because think about it. For years, we've relied on just a handful of trusted methods to guide neural networks toward intelligence. But as we push into this wild new realm of trillions of tokens and tens of billions of parameters, well, those trusty old methods, they're really starting to show some cracks.
To unpack all of this, we'll follow a quick roadmap. First, the AI training bottleneck. Second, enter muon and SOAP. Third, fixing slingshot instabilities. Fourth, the layer-wise system solution. And finally, the new pre-training champions.
Starting off with Section 1, the AI training bottleneck. Let's look at the fundamental problem holding back modern AI training. Okay, so for years, the AtomW optimizer has basically been the undisputed heavyweight champion of language model pre-training. It's computationally simple, it scales super well, and you can easily split it across thousands of GPUs. But there's a massive catch. When you're training huge mixture of experts architectures, like the 72 billion parameter models tested in this research, and you're pushing hundreds of millions of tokens, AtomW finally hits a wall and starts losing its token efficiency. See, in an MOE model, the network uses sparse top K routing. That basically means individual expert layers only see a tiny sliver of the global batch of data, while the dense shared parameters are forced to process the entire massive batch. So when you scale up to a global batch size of, say, 25 or even 100 million tokens, AtomW hits what researchers call a critical batch size. It just stops scaling effectively, giving us diminishing returns and some pretty nasty numerical instabilities.
Moving to Section 2, enter muon and SOAP. This brings us to the new heroes in the optimization space.
The really crucial point here is understanding exactly why AtomW fails at this scale and why these newer optimizers are succeeding. It comes down to this. AtomW is an element-wise optimizer. It treats every single parameter update totally independently. Honestly, it's kind of like trying to steer a massive cruise ship by independently tweaking a million tiny little rudders without ever looking at how they actually connect. It completely ignores the structural correlation of the neural network matrices. But higher-order methods like muon and SOAP, they perform matrix or tensor-wise computation. SOAP uses these things called Kronecker-factored statistics, and muon uses Newton-Schultz iterations. I know, the math sounds a bit intimidating, but in simple terms, it just means they look at the geometry of the entire network rather than isolated parts. They capture the big picture, and that theoretically allows for much larger, far more accurate steps toward a lower loss. And this brilliantly illustrates what that big picture math actually achieves in practice. When you look at the training loss, muon, even when running at double the batch size of AtomW, manages to maintain a beautifully stable lower loss curve. It's thriving exactly in the zone where AtomW begins to choke. By keeping that structural awareness of the matrices intact, muon is able to normalize its updates independently of coordinate-wise scaling. That makes it incredibly resilient to the sheer noise you get with massive batch sizes.
That brings us to Section 3, fixing slingshot instabilities. But hey, let's not break out the champagne just yet. These new optimizers have a fatal flaw we've got to fix.
So when the NVIDIA team pushed SOAP into this large batch multi-billion parameter regime, they immediately hit a brick wall. A severe early training instability. The main culprit? Something called a stale preconditioner. Because calculating these massive 2D matrices is super computationally heavy, the standard implementations only update the mathematical eigenbasis every 10 steps or so. Plus, they usually completely exclude the current step's gradient. This creates a really nasty lag. Now, the loss landscape of an AI model changes incredibly fast during early training. If you apply a preconditioning matrix that's based on outdated gradient statistics, your optimization trajectory is going to drastically rubber band or essentially slingshot way past the optimal point.
And you can see just how visceral this failure really is. Look at those massive, chaotic spikes in the blue loss curve.
and the red gradient norm curve. That is exactly what a mathematical crash looks like in real time. For a smaller model, sure, these oscillations might eventually dampen out, but when the researchers scaled this all the way up to an 8 billion parameter dense model, this lag became completely catastrophic. It led to total training divergence. The model basically just forgot how to learn.
So the researchers realized pretty quickly that just updating the math more often wasn't going to cut it. Instead, by forcing per-step eigenbasis updates that actually include the current gradients, and by bringing in a technique called KL shampoo for covariance estimation, the NVIDIA team managed to completely eliminate those terrifying spikes. Just look at the orange curve now. Smooth, stable, completely flattened out. This KL divergence regularization acts as this crucial secondary layer of stability. It effectively safeguards the training dynamics against all that floating point noise.
Now for Section 4, the layer-wise system solution. Okay, the math is fixed, but fixing the algorithm is only half the battle, right? We also have to tackle the hardware constraints.
And here's the system-level nightmare we run into. To train massive AI models across thousands of GPUs, we rely on distributed training systems. Think FSDP, or fully sharded data parallel. These systems are great for saving memory. They take a model's parameters, flatten them out into 1D vectors, and then chop them up evenly across all the GPUs. But wait, remember what we just said about mu and SOAP? They desperately require fully intact 2D matrix structures to compute their advanced geometry. So if we use standard distributed training that slices up those parameters, we literally break the very 2D structure that these higher-order optimizers need to function.
So how do we keep the matrices intact without instantly running out of memory? Well, NVIDIA's engineers built a highly custom, layer-wise distributed optimizer right inside the Megatron LM framework, and it works in 3 really elegant steps. Step 1 is load balancing. Instead of chopping up individual matrices, entire completely intact parameter matrices are sorted by size and then dealt out to different GPUs in a round-robin style. Step 2 is independent updates. Each GPU runs that heavy muon or SOAP math only on its fully intact specifically assigned layers. And finally, step 3, overlapped parameter all gather. As the model actually computes its forward pass, the GPUs asynchronously fetch the newly updated matrices from one another. This effectively hides the massive network latency behind the computation itself. It is honestly a masterpiece of systems engineering meeting pure algorithmic theory. Finally, Section 5, the new pre-training champions. So, with those mathematical slingshots stabilized and the hardware sharding systems perfectly aligned, what do the final results actually look like?
When we look closely at the benchmark data from the paper's 8 billion parameter model, it's clear. When scaled up, muon decisively beats AtomW. Just check out the coding and math scores. On human eval, muon running at a 2x batch size jumps to nearly 66%, which just completely leaves AtomW in the dust at 57.6%. And on the Math 500 benchmark, muon reaches a staggering 80.2% compared to AtomW's 75.6%. By holding onto that structural awareness, muon absolutely shines in complex tasks that require deep, rigorous mathematical reasoning and logic.
But this isn't just about getting slightly better benchmark scores, it is really about raw, unprecedented scale. Look at how beautifully muon and SOAP scale up to 4x the baseline global batch size. This is a massive breakthrough. It allows researchers to confidently wrap up training to an astonishing 100 million tokens per batch without sacrificing model quality and without crashing their clusters. Basically, we can now train significantly larger models much, much faster.
Ultimately, when putting muon and SOAP head-to-head, the paper comes to a very specific conclusion. They note that the KL SOAP variant emerged as the most effective approach overall. So in scenarios where memory footprint isn't a limiting factor, they actually recommend KL SOAP over muon. It turns out that while both are incredible leaps forward compared to AtomW, KL SOAP holds just a slight edge in reducing training loss. It should absolutely be your go-to optimizer. That is, assuming your GPU cluster has the massive memory required to store its full precision preconditioner matrices.
So I'll leave you with this thought to ponder. For the last few years, our progress in AI has been somewhat throttle limited by how much data our optimizers can digest at once before they mathematically choke. But if NVIDIA's new implementations of muon and KLSOAP are fundamentally removing the speed limits on how fast and wide AI models can learn, effortlessly digesting 100 million tokens in a single breath, well, what entirely new frontiers of intelligence are we about to cross? Thanks for joining me on this deep dive, and as always, keep your eyes on the horizon.